cosmic rays and gamma rays, X-rays, and so on. The visible light extends from 0.3 micron to 0.7 micron, 0.2 to 0.7 as a visible spectrum. However, thermal radiation from anywhere from 0.1 micron to 100 micron. So -7 means this is 1 micron, this is 0.1 micron, this is 2 basically 100 micron. This one, this line. So the thermal radiation anywhere from 0.1 micron to 100 micron. So it's like 3 order of magnitudes. And radio waves are all, so top is the wavelength, bottom is the frequency. So wavelength is small, frequency will be high. So this is the basically the ultraviolet rays and so on, X-rays and so on. It's all in this regime. So very high frequency and low wavelength basically. Okay, so look at the thermal radiation itself, 0.1 micron to 100 micron. The visible spectrum is 0.3 micron to 0.7 micron, like this. So that can be divided, which we know that it's violet is the lowest wavelength and highest frequency, and all the way to indigo, blue, green, yellow, orange, and red. And if you start seeing some red, I can actually show you the thermal radiation. You can see that it's around 800 Kelvin, but we will see that later. But even on the beyond the visible range, the near infrared, you can break it up into 3 regimes. Near infrared, the visible spectrum, ultraviolet, near infrared, intermediate infrared, far infrared. We cannot see them, but there is still energy left, thermal energy are there in this particular spectral bandwidth. Okay, all right. Now I will not go into the actual how the sigma is spread in the frequency, but we will go and first we'll, historically speaking, we want to prove that the Stefan prediction that the radiation energy is more proportional to T to the power of 4. He didn't believe it himself, but he was trying to understand it. He wanted to support. So Boltzmann supported him very well, and he derived using thermodynamic principles how thermal energy is proportional to T to the power of 4. So let's just do that very quickly here, how he derived it. So let me just go here a little bit. So I want to see that a little bit more. Let's, all right, let's see. Okay, so what Boltzmann assumed as a working fluid in a Carnot cycle is basically the photons, photon gas. All right, so the del Q, if I put it in just let's assume that there is a volume here, the photon gas are inside, and there is a plunger here. You can change the volume here, V, and then the pressure and so on. So this is equal to if I change the internal energy plus the work done. So if I put in here that you can work done by the plunger, which is equal to P dV. Now there are 2 things in there. This is the extensive property. The intensive property is the internal energy E. It's internal energy per volume. So I can write T ds, which is dq. ds is the change in entropy, which is the path independent variable entropy. Even though the heat is not path independent, but the TDS, the ds is path independent. This is equal to T eV. Now thermodynamic statistical mechanics, when you have the photon gas which is traveling at a velocity of speed of light, P was you can prove in statistical mechanics is equal to internal energy divided by 3. So this is bombarding these walls, creating a pressure here, and that pressure that is felt by the wall is equal to the internal energy divided by 3. So I can read this as internal energy over 3 dV. Now I can write this dEV, E as a function of temperature. So I can write this as d dt V d dt dt. In other words, dt you are taking as a constant pressure, of course, plus there will be E also coming in because dV, I'm taking the dV dt, isn't it? So so the E dV will be there, plus E over 3 dV. So this becomes V d dt plus 4 over 3 dV. And so let's take the, so I can say that ds is equal to, I can bring the t here. All right, let me take the derivative with respect to t. Let's say, in other words, this if I have the ds, so ds can be given as ds dv at dt and ds dt, I'm sorry, dv dt. So this is the equation, this is constant t, this is constant t. So this, you can say that I can equate this to this. So my ds dv, that is proportional to dv, isn't it? So it's like 4 over 3 t. Oh, I'm sorry, this should be E over dv dt. Okay, 4 3 E. So E over t. Similarly, so ds dt is, this is proportional to t. So ds dt is proportional to v over t d dt. Everybody following this? Okay, so we know this, so I can further differentiate this with respect to t, and this will be differentiated with respect to d over dv. If I do that, what do I get? So if I perform that d square, so my ds dt is v over t d dt, and ds over dv is 4 over 3 e over t. So if I take the derivative with respect to v, so what happened here? It says this is just the v only, so this 1 over t d dt. Okay, so that should be basically equal. So suppose this is what is second identity. If I take the derivative with respect to t, then what happens? Minus 4 over 3 e over t square. That's one term, isn't it? That'll be there. Plus, I am trying to take with respect to e. So 4 over 3, 1 over t dt. So so basically these are both should be equal to the same. So 1 over t d dt is equal to I take the 4/3 out. 1/t d dt minus E/t square. Everybody following this? Because this is the same, the identity is the same, I can equate them. So this right hand side here is equal to this right hand side. That is how I have equated that. So what exactly this means is I can bring the d dt, I can bring it on the other side. So 1/3 dE t/dt. In other words, I'm bringing this over here, so it becomes minus 1/3, isn't it? So this minus minus gets cancelled. This is equal to 4/3 E/t square. Everybody follow that? So 3 gets cancelled. So d/e, the t and the t gets 1 cancelled. 4 dt/dt. Okay, so if you take the derivative, integrate, log the internal energy is equal to T or proportional to T to the I'm saying log 4 log T or log T to the power 4. So E is proportional to T to the power 4. So the internal energy associated with the photon gas, internal energy is proportional to T to the power 4. So by purely thermodynamic consideration, Boltzmann was able to say that after all, his teacher was not wrong. So anyway, Stefan said the internal energy is A T to the power 4. So this is the energy basically. So he just said if it is radiating out with the photon gas, that energy coming per unit volume has to be proportional to T to the power 4. So I hope you followed. If you have any questions, so let's go back. There is something more to understand. Even the Wien's law can also be proved right from here. Let's just look at this. So suppose I want to get the maximum. In other words, dq is maximum. In other words, TdS, when does it get the maximum? Where maximum internal energy? When do we do that? So we can go back and look at the equation earlier. 4/3 EdV plus VdE, because dt dt gets cancelled. Vd is 0. So what happened here? So dV over V, so it becomes, okay, 4/3 EdV is minus VdE. Okay, so, and we can again do the same thing. So 4/3 dV over V is minus dE over E. Okay, so basically because of the negative, I can bring the negative here. So we can just 3/4. So it's basically what I'm saying is E 3 to the power 4 multiplied by YV has to be a constant. Since the volume is proportional to the wavelength, because remember the black body, I will just show that later on, is the volume has to be proportional to the wavelength, because it is trapping at for that particular frequency it is radiating at. So I can say that E 3/4 V lambda cubed, and E is proportional to T to the power of 4. So T cubed lambda cubed is a constant. So lambda T is a constant. So not only using thermodynamic principle, we can say the internal energy is T cubed, I mean proportional to T to the power of 4. We can also prove that the maximum energy can be given by lambda T is a constant. And we can, so even without getting the real distribution of the energy, one is able to see this Wien, this is Wien's displacement law. Displacement law we can prove by purely by thermodynamic argument. It's an interesting exercise. Are there any questions on that? Any questions? Okay, all right. So let's go back. So basically what we did is, the Stefan's experimental results are can be supported by thermodynamic argument. So he had a little bit more faith in it. But the problem was not completely solved because he still had some issues with this discreteness of this whole energy spectrum and so on. So he wasn't sure. And then again, the discretized particles, if I associate energy with it, how can we determine those? Is it really distributed? How? Because optically we are able to get those the 7 colors out of it. So it is able to be you are able to dissect that energy spectrum. So there must be something more. So that is when Max Planck came into the picture. So let's just do exactly how he was, even before that people were trying to formulate this problem in a way. So let's just argue that particular argument to formulate the radiation spectrum, how it's distributed, energy is distributed. Okay, so that is where this comes in. So what exactly is a black body? Black body is you have a body and there is energy is getting in and it has multiple reflection. It doesn't go out, it gets trapped. So we showed yesterday, we already said that the length of that, if it is a one-dimensional propagation and it's a small hole gets in, so it's wave is reflecting back and forth, doesn't escape. So that length of that particular body, one-dimensional body, has to be some discrete number of the half the wavelength when j is equal to 1, 0, 1, 2, 3. Now this is where an interesting argument occurred. Since the number of particles, remember the Avogadro's number is 10 power 23. If I have 1 gram mole of the gas here, he's proved that it's 10 to the power 23, which is very large number. So we can assume j to be a continuous variable. So remember, it is all three-dimensional problem. However, we want to make sure that it's only propagating in the positive direction in all the 3 dimensions. Suppose I convert this whole variable into a r theta phi variable in a spherical system. So in 3 dimension, this x, y, z has to be positive, because that is what the wave propagation wave has to be positive number. You cannot have a negative number. So what exactly is the proportion of the energy? I'm going to count how many such particles exist. So I need to count 1/8 of the sphere. So what exactly, if I have a sphere of radius j, how many such particles exist in a small radius dj? Remember, I'm going to continuous j, even though it was discrete, I'm going to consider this as a continuous variable because the number of particles inside is very, very high. So what exactly, how many such particles exist in this particular small spherical volume between j and j plus dj? So I get 4 pi j square dj number. divided by 8, because everything has to be positive. J has to be positive, so it cannot have, so it is only between 0 and, so let's assume this variable is phi and this azimuthal variable, this is psi. So phi is varying from 0 to this is z, this is 0, is varying from 0 to pi over 2, and the psi is also varying from 0 to pi over 2. So it's 1/8 of the whole spherical volume. And these particles can also be, they are doubly polarized. There can be linearly, horizontally or vertically polarized. So there are two possibilities. So you got to multiply by 2. So if I want to say number of particles, so number of particles between these energies, sorry. So the number of particles which satisfies the criteria. So number of particles which will have the, it'll have a, what do you call that, the waves will be reflecting back and forth. So multiple reflections, it will not be able to escape. So 2 multiplied by 4 pi j square dj divided by 8. So basically pi j square dj. So that's the number of particles. Okay, now there's an interesting transformation that I want to account. So the dj, so how much is the distribution of the particles in the dj? So I'm going to call this as gj dj. Yeah, okay. So yeah, I don't know exactly what he is doing. Okay, that I already got it. So dj is going to be j square dj. So the distribution is like pi j square will be my distribution number. Out of all the things, this is my distribution number. So I'm going to convert this into the wave number. So how do you convert? This is like a space variable. So how do I convert this into a dj will be equal to, so my the space variable is related to the frequency variable by the velocity of light. Okay, so my dj, so let's say C over dj. So dj is going to be minus, because 1 over j, so dj is going to be, so 1 over lambda. So the v, the frequency is again let's say 2l lambda square over dj d lambda. So g, so I convert this whole thing into, in terms of lambda will be equal to, because of this L square and then again L. Remember, this L is going to be, see, L is j lambda over 2, isn't it? So my j is 2L over lambda. So dj will be minus 2L will be lambda square, d lambda. So that is how I got this. From the original assumption, this is the L has to be the space of that, in the space in that domain has to be equal to j lambda over 2. So the dj will be 2L. That is how I got that. So I convert everything into the frequency. First of all, I'm going to take a lambda domain, so which is equal to 8 pi. But the important thing is I'm converting everything into a frequency distribution. So let's just do that quickly. So instead of, I can relate everything. See here, the J space was converted to the lambda space now. And from the lambda space, I can go to new space using this relationship. In other words, d lambda will be equal to, so C over lambda in nu, isn't it? So d lambda will be minus C over lambda square d lambda. So I converted from dj to d lambda space. From d lambda, I can convert to d nu space, the frequency space. So that is what I've done basically. So let's just, and again, I'm just counting spaces and finding out what the distribution will be. So let's go to the next slide. Okay, so I got in the frequency domain, what is the distribution function between the Gj is my, like, just like a density. I'm sorry, d nu is going to be 8 pi over c square nu square d nu. So I got everything. The 8 everything came because of the 4 pi square. Okay, so that is how the 8 came on. Okay, but anyway, if I, so idea behind it is each such particle here. So this is the number of particles in a small space between nu and nu plus d nu. So that's what this is. Between the frequency of nu and d nu, this is the distribution of energy. Suppose I attach an h nu free energy per photon. So what happened? I had to multiply. So my energy density will be 8 pi c square nu h, of course h will be there, d nu. So if I want to integrate from all the frequencies from 0 to infinity, I will have to do that. If I do that, everything else is a constant, this is going to blow up. So the high frequencies will be completely, will be diverging. So this is what is called classically, if I attach pure energy for each particle, so this is what is called ultraviolet. It was famously called ultraviolet catastrophe. If you Google that, you will find it. So RBS acceptable. So what did Max Planck did? He was a, so let's say that you knew that per unit the distribution of the frequency is 8 pi c squared okay, is it c squared or c cubed? I think it's c cubed. Let me just check it. Yeah, I'm sorry, this should have been c cubed. So this is c cubed. Okay, that's what I thought. So should be c cubed. All right, so 8 pi over c cubed so instead of, this is nu square. So instead of h nu, suppose I'm just doing an average h nu. This average h nu was determined using Boltzmann's distribution. What does that mean? Basically, what that means is, suppose I define a probability of n particle in an energy spectrum as an exponential minus, each particle is n h nu divided by kT divided by over the whole of n is equal to 0 to or 1 to infinity of exponential. So this will be a probability distribution, isn't it? So this will be a probability distribution of having n particles in a particular volume. Okay, so what exactly is the average energy then? Then my average energy will be for all particles n0 to infinity h nu exponential n h nu over kt divided by exponential minus h n nu kt. So this is he used. This is a brilliant stroke. If I use that, I get the average energy per particle will be h nu. Same thing will come because this can come out for h n is equal to 0 and n is equal to 1. It can come out. That's the reason h nu is coming out. So E is equal to h nu divided by. You can perform this particular summation. It's an exercise, but I'm not going to go through this. H nu divided by kt minus 1. So instead of attaching h nu, if I divide by this number at a very large number h nu, this also gets large, so it doesn't blow up. It will converge. So that is a brilliant stroke. And with all this assumption, you will be surprised how close the number comes out to be. So if I perform this integral, so I go back to my g nu and attach the u nu. So my energy contained in the small band nu plus d nu u is h 8 pi over c cube h nu cube. Remember, that is what was blowing up, and divided by exponential h nu divided by kt minus 1. Okay, so let's just do an integral of that. So what exactly is 0 to infinity of u nu d nu? So let's just do that one easily. So let's just very interesting here, but how will I do that? So h pi h over c cubed. I'm going to assume h nu over kt as x. Okay, so here, so what happens here? So kt, so I can do this one. So nu cubed and everything can be converted into this. So this integral becomes 0 to infinity of x cubed dx. I think it's x cubed, I think. E to the power of x minus 1. And this is a very classic, very well known from Fourier series and stuff like that. This is pi over 15 by 15. So I can convert this everything into. So what happened here? So how do I write this u infinity d infinity? Now this is, I'm just integrating the whole energy contained in the spectrum. So it will be like 8 pi h divided by c square c cubed kt over h to the power of 4. Remember, the kt comes in to the power of h to the power of 4 because I'm assuming the x cubed, so x cubed comes out. That is the reason the fourth power comes in, so that you can, that's all algebra. And here integral of 0 to infinity x cubed dx divided by a to the power of x minus 1. Because x again I just assume to be kt over h. And this is nothing but pi over 15. So the whole thing comes out to be 8 pi to the power of 15, 5. Yeah, because there's 1 pi here, so this pi over 4, pi over 4, that's why 8 pi 5 came in, and k to the power of 4 divided by 15 c cubed h cubed t to the power of 4. Now, this is not Boltzmann constant yet. Stefan Boltzmann law, this is only a density. In other words, this is the density of the energy, that is, the total energy, density of the energy. So this is just like a joule. So energy only, not watt, not just per second. So you got to convert this into what is the flux coming in. So you got to use by, I'm not going to do kinetic theory, but let's just see what exactly what that is. So I'm going to say the integral of u infinity, t infinity. This was the density of the, and we got this is equal to a t to the power of 4, where a is 8 pi to the power of 5, k to the power of, k is a Boltzmann's constant. I'll show you exactly what they are all, and 15 c cubed divided by h cubed. And then if I put all the number in there, it becomes 7.566 10 to the power of minus 20 minus 16 joule per meter cube Kelvin to the power of 4. So basically it's a per, see, remember that's a density, isn't it? So that's a density. This is the energy density, and that that is the reason that m cubed comes in. So, and then joules is only energy to the power of 4. Now, if I use, what exactly is the flux energy coming in? In other words, each particle is traveling at velocity of c. So what exactly is the flux? It find out that you multiply the energy density multiplied by the velocity divided by 4 from the kinetic theory. This is from kinetic theory. So if I a c over 4, if I do that, this becomes sigma t to the power of 4. So c is meter per second. Anybody can do this for me? 7.566 10 to the power minus 16 minus 16 was it? Yeah, minus 16 divided by 3 10 to the power of 8 divided by 4. Can anybody do this? I mean, obviously you get 5.67 10 to the power minus 8 watt. Because remember, this is meter per second. That was joule per second is watt, and meter gets calculated as a meter square, Kelvin to the power of 4. So that's a sigma. So basically, by assuming that a black body radiation is like a trapped wave coming in, then you count the number of particles, attach an energy to each particle. If I had assumed simple energy per particle as h nu, it would have blown up. So Planck used the average energy per particle, using average energy being calculated using Boltzmann's distribution of the particles, the boson, the photon particles, and reasonable energy distribution. Then we are able to get the Boltzmann's equation and its distribution also we can find, and from there it's where we get the how is distributed. So let's just go very quickly. So using that, so remember we got, if you look at this formula here, 8 pi c cubed h nu cubed is all this here. So that's nothing but the density you have to multiply by c to the power of c over 4. Then you get this behavior here. We'll do that maybe next class, but we'll just do this one. What's happening here? Okay, so we can convert that. See, remember we just integrated that, but if I just got the distribution of the energy, you can relate that per a particular lambda is given by this at a particular temperature is given by this. So this is nothing but the monochromatic spectral emission at a particular lambda. This is given by this, basically that equation that we saw. So there are two constants, C1 and C2, based on the Boltzmann constant and the Planck's constant, H and K. So you can really relate that back, and then you can take the, how does this, when does it get maximum, and you can also prove this is the nothing but the Wien's displacement law. So we will do that next class, next Monday, and then any questions? Okay, I'm going to stop the oh, Jesus, what happened here?